Okay, so next up we have Craig Gidney from Google, who will be talking to us about magic state cultivation.
Right, so I'm told that my job is to make the previous talk irrelevant. Right, so I'll be talking about magic state cultivation, which is basically, I don't know if I want to say new, but an improved way of making magic states that's much cheaper. So for some historical context, here's a screenshot from a talk or a YouTube video of a talk given by Austin Fowler, who's one of my coworkers 10 years ago in 2014, or I guess 11 years ago now. And in this screenshot, he's got these 3D diagrams of the various operations you'd want to do in a computation. And on the left, there are the Cliffords, and on the right, there's the construction for the T-gate. And the main thing that I want you to notice is that the T-gate construction is really, really big. In fact, 2 years before this, he had put out a paper with John Martinez and a couple other people talking about like how would you do surface code computation in 2012 at least. And in that, they did an estimate of how expensive it would be to do like factoring, and like 99% of the space-time cost, like 99% of the work being done by the qubits was running these magic state factories. So 10 years ago, this was like your whole computation was magic state factories. Anything you could do to make magic state factories fewer was what was going to make your computation better. Now, over the past 10 years, there have been a lot of improvements to this that have been accumulating and slowly chipping away at this idea that the main thing that you should focus on is the T-states, or the T-gates. And I don't want to say that these are like amazing, groundbreaking insights. They're sort of very basic observations that people just overlooked for surprisingly long. So, for example, in this picture here, these like pointy bits are the magic state injections, and the top is like the future, and the bottom is the past. So it's doing the injections at the end. You don't want to do the injections at the end because then you can't throw out the ones that look bad. And this was pointed out by Lee in 2014, which is that post-selecting your injection makes it way, way, way better. Like instead of starting at 1% error, you get to start at 0.1% error, and then distillation will multiply that every time you apply it. And then there was this switch that happened in the field from using braiding to using lattice surgery, which is essentially, instead of the logical qubits being kind of wrapped around in between holes punched into an open ocean of surface code, we started putting them inside boxes so they didn't interact with each other so much. This is like, instead of needing 12 d squared physical qubits per logical qubit, now it was 2d squared. In 2019, Daniel Latinsky pointed out, you know, we're hosting this distillation in a surface code, and that surface code needs some big distance, and this is the big reason that this is expensive. But some of the errors that happen in the surface code actually get caught by the distillation. So for all of those errors at those places, you can kind of squish the surface code a little bit, save some code distance. You can take this even further, and you can have your decoder report a confidence on its prediction, and then kind of squish everywhere, because a state preparation task is something you can try again. I'll note, this is a very, very different list from what you would make for the theory advances in magic state distillation over the past 10 years, which are more about like, you know, improving gamma or maybe better thresholds or things like that. Those things are very interesting in the asymptotic limit, but when it comes to practice, they're sort of too far into the asymptotic limit to matter usually. 2014, we kind of had this enormous box. And then from the previous slide, improvements, we had something of the scale of this box with about the same reliability. And what I'm going to be talking about in this talk are these like long, narrow poles where we're going to be doing something very small. We're trying it many times, and it's not quite at the same level of reliability yet, at least assuming this much noise. So here's an overview of a magic state cultivation. So this is the same type of diagram that Austin was showing, where time is going from bottom to top, and the colors are showing places where there are topological defects. So we're going to start with a color code, very small color code. We're going to inject a magic state into it. Everything's going to be post-selected at this point, and then we're going to start doing checks of the state. And then once we get the state as good as we want it, we then need to get out of this small color code because it's not reliable enough to keep the state. The state's going to be far more reliable than the per round error rate of the code with no post-selection. And this is actually surprisingly the hardest part of the protocol. So one of the reasons that I sort of waffled on saying this is a new idea is almost all the pieces of what I'm going to be discussing were known beforehand. And kind of what's different is I liked one of the reviews that I got when I submitted the paper here to QIP, which is they said that the strength of the paper is execution. And it is very much like I took a bunch of existing ideas, or we took a bunch of existing ideas, and we kind of shaved off factors of 2. And when you're post-selecting, shaving off a factor of 2 is in the exponent. And so it can make the difference between it's too expensive and it's just something that you would obviously do. Anyways, in 2020, Christopher Chamberlain and, I don't remember the other author, I'm sorry. They pointed out if you have a color code, you can measure in Clifford bases by preparing a GHG state and applying a transversal Clifford conditioned on the GHG state. So with each gate controlled by one of the qubits from the GHG state. So you get phase kickback into the GHG state, and then you measure it in the X basis in order to get the measurement result. Actually, I got an email later on from someone called Godo that says that they had the idea in 2016, but the paper's closed access, so I have no idea if they're telling the truth. I only really found out about this idea last year at, I believe it was March meeting when Itagawa et al. Gave a talk where they had basically taken the Chamberlain idea and done it a little bit more compactly. In particular, they showed that it worked at 10 to the minus 3 noise, whereas this previous result showed it only worked at 10 to the minus 4, which, because I'm very practical minded, 10 to the minus 4 to me sounds like not going to happen. But maybe it will. And something I want to point out, if you look at the circuit diagram and you count the number of A's, which is what their letter for T for some reason, there's 15 of them. And if you start putting Z errors next to the A's, there's exactly 35 triplets of errors that cause it to fail. And if you're familiar with distillation, you know that the 15 to 1 factory has 35 distance 3 errors. So this is really just a rearrangement of the 15 to 1 distillation circuit, where instead of encoding into a 15 qubit code and then applying them transversally, we've kind of folded up the circuit a little bit so that it's inside a color code. And the major benefit of this is, at least for a planar architecture, we want it to run like a color code or a surface code anyway. So it's making the distillation fit better into what we were already going to do. This does kind of raise the point of like, why did I call it something different if it's just the distillation identity? I do think that is sort of qualitatively different, but here are sort of the rough reasons why I gave it a different name. Really, it's not like you're making a whole bunch of states and throwing out a bunch of them in order to leave a couple behind that are better. It really feels more like you're gradually improving one state. In particular, the fact that these are gates instead of states. The fact that the operations are inside of a code instead of hosted on top of codes. And in particular, the fact that because it's inside a code and because we're going to be post-selecting very hard, there's sort of a wall that you can't get past where the cost goes exponential because you're throwing away too many shots. Whereas distillation, you can just keep chaining it, nothing stops you. And the other major reason is cultivation sort of ends with an exciting escape scene, whereas distillation just kind of ends with like, all right, everything has been big enough the whole time. So it's just sort of a given that it'll be okay. So compared to these previous papers, what are the main things that we improved? First of all, in the Chamberlain paper, they start with the color code at the distance that they want to target. And in the Itagawa paper, they just stay at distance 3. And what we do is we just grow the color code incrementally basically, as the state becomes more reliable, we grow the code to accommodate. This reduces the number of gates that you need in the early stages, and when you're post-selecting, all of these constant factors go into the exponent of your rejection rate or your keep rate, and so this is very important to make these sorts of improvements. The other major improvement is the phase kickback measurement, where you make a cat state and then do transversal gates. We do that a little bit more cleverly, where we pair two of them up and time reverse one of them, and a whole bunch of gates cancel out as a result of this. And this is basically the reason that we can get to distance 5 instead of being stuck at distance 3. We also have a better color code cycle from a previous paper that I worked on with Cody. And the other thing, which I don't really think of as an advantage of the paper, is more like a cost of the paper, is the way we get out of the color code and into a surface code is by this technique that we had to make called grafting, which I'll talk a little bit more about. And also we do the decoding in a particular way. Like in the Chamberlain paper, because they were doing not 100% post-selection the way that we are, they had to have like a just-in-time decoder that had to finish what it was figuring out before the next round could begin. And this is a very difficult requirement to meet in practice. And all of this adds up to, instead of this whole thing limiting at 1 in 10,000 error, it limits at closer to 1 in a billion error. So the first thing we do is a state injection. This is the figure straight from the paper. I'm pretty sure it's using the wrong basis, so it looks incomprehensible. It doesn't really matter how you do the injection. I tried 3 different injections in the paper. They all behave basically the same. If you have a favorite color code injection, you can use it. Then there's the actual cultivation phase, where we check on the T-state using these phase kickback measurements. We keep growing the color code as needed. We measure the stabilizers of the color code to prevent correlated errors across the T-state measurements. We'll keep going until we kind of get close to the cost wall, and then we escape. Here is a circuit diagram of the kickback measurement. Here's a larger circuit diagram of the larger kickback measurement. I'm going to open this. I'm going to go over to another tab. I just want you to see, it's very obvious if I just step through the circuit, kind of what it's doing. So I just want you to notice these would be T gates instead of S gates in the actual circuit. The CNOT gates travel towards the middle, where the measurement happens, and then they go back out towards the sides. One of these is sort of the normal cat measurement. The other one is the time reversed one. Okay, that just tells you sort of the style of the circuit, and it sort of tells you how it would scale if you went to bigger distances. So once we've done that cultivating, we have some code that contains a really, really good T-state. Like this T-state might have an error rate of 1 in a billion. A distance 5 color code does not have a per round error rate of 1 in a billion. It's hundreds of times worse than that. So we can't stay here for even one round without post-selection to sort of paper over the difference. So we have to grow it. The natural thing to try is to grow it as a color code, which you do by preparing bell pairs. So here are these cyan wedges are bell pairs. Unfortunately, the decoder that we have access to is not good enough for this. We have evidence from very expensive decoders that this should be good enough, but we don't have the decoder that actually does this efficiently. So it's very possible that someone could write a better decoder and make this work. But because we couldn't do this, we get into the hard part of the paper, which was how we actually did the escape into the surface code. So first I'm going to describe this topologically. You may have heard before that at the corners of surface codes, there is a type of topological defect called a twist. So here I'm drawing them as these 4 squares. Basically what we're going to do, I'm going to describe this in reverse. We're going to fold this twist in. So we end up with a part of the surface code that's covering itself. So at this location, there's 2 surface codes on top of each other. And it's well known that 2 surface codes on top of each other are equivalent to a color code. Then we're going to retract these other twists inward, leaving behind only the color code. But actually, we're going to run this in reverse in order to produce a surface code. Probably the most interesting state is this intermediate state where this one here, where you have a color code in the corner and you have a surface code kind of popping out of it. This is very different from what people were doing in previous papers to get the state out of the color code into a surface code. In those papers, the color code, instead of pointing inwards like this, would actually point outwards. And this corner here would actually have to be all the way up here. Basically, they were doing lattice surgery between the surface code and the color code. And the downside in this context of doing lattice surgery is it has the distance of the smaller code. And our smaller code is too small to support the state we want. We want to immediately be as high in code distance as we want in order to reduce the number of small fault distance chains that are present. So we made this alternate version where there's a color code and a surface code, and they're attached together in a way where they have the distance of the surface code. I'm kind of proud of this, and I kind of hate it also. I would really prefer the solution where someone just makes a better color code decoder. It would be so much simpler. And probably the error rates would be ultimately better because there's just less stuff happening. Yeah, so here are sort of the drawn out versions of each of these things. The final state ends in this funky looking code. You can measure all of this out in the X or Z basis and then reset it back and replace it with a normal surface code at the cost of temporarily reducing the code distance if you really want to get rid of this, which you probably do. Ending in a nasty state is not really the major problem here. The major problem is all the complication that leads up to it. We also have to do some funky decoding for this. So I tried a whole bunch of different ways of decoding this, and the one that I found that worked the best and was, frankly, the simplest was pretend that it's actually matchable by just introducing fake extra nodes. So in a surface code, you naturally have matchability, by which I mean when you insert an error, you'll set off a pair of stabilizers. So errors set off even numbers of things. Color codes aren't matchable because if I put an error, for example, here, I'll set off these 3 adjacent stabilizers, and 3 is not 2, it's not even. So what we do is we just introduce these fake nodes that represent both of these excitations, and we tell the decoder, hey, there's an error that sets off this green node and this double node, and also these other 3 pairs that are present. And then we just post-select where we say, like, if a green node ever goes off, throw it out. And this papers over the fact that this is really not a correct way to decode a color code. Don't try this if you're not post-selecting. You'll get terrible results. To sort of summarize the decoding, we just did the hackiest thing that we could possibly do that would work. Here is a plot that sort of shows as you execute the protocol, how many shots are you losing, and also how many qubits are active. So this blue curve is showing as we run, we're producing detection events. So because we're post-selecting everything that could go wrong, anytime something goes wrong, we have to start over, and so we lose shots. So you see this sort of consistent decrease from the cultivation bit. And then once you get into the thing has grown part, the rate kind of tails off. This is basically because we're turning off the error detection. And this big jump here is when the decoder finishes computing its confidence of what happened back here, because we assume that that takes 10 microseconds. To be clear, this is not actually like we were running the decoder and seeing this. This is like I said plus 10 in the code, and so that it's over here instead of here. But this gives you a sense of, first of all, we're post-selecting quite hard. Like there's only like 1% of shots left at the end here. The major cost of this protocol is just trying it enough times to get a really good result. You have a sliding scale of how strong the requirements you're placing are. So you can choose to allow more shots through at the cost of reducing the reliability. Also, because there's so few qubits active over here, you can technically run many of them in parallel and only keep the one that looked the best. So there's a whole packing problem here that I'm not really getting into. So benchmarking. We have this protocol. How do we test how well it works? it's actually very annoying. So because of the escape stage, we grow to this very large code. That means the circuit has hundreds of qubits in it, so you're not going to be able to do state vector simulation. We have T-gates, so you can't do stabilizer simulation. It's an error-correcting code that is incredibly interconnected, so you can't do really fancy stuff like tensor network simulation. You could do what's called stabilizer decomposition, where you basically simulate a superposition of stabilizer states. There are papers that do similar size circuits with similar numbers of T-gates, but they're way too slow. Like, I want to do Monte Carlo validation of this circuit, which means I need billions of shots if I want to see a 1 in a billion error rate. And these techniques take like a minute per shot, and I mean, technically I have access to a lot of compute, but I don't think they would let me spend that much money on this. Instead, what we did is we completely cheated and we replaced the T-gates with S-gates. So the idea here is the only change in the circuit is you literally search replace T with S. So the structure of the circuit overall is very, very, very similar. And it makes it a complete stabilizer circuit, and you can simulate it very easily. And the main question is, like, how accurate is that? So here we did a state vector simulation of just the beginning, before the escape stage, and just at distance 3, which you can do a state vector simulation. And you can see there is a noticeable difference. So the T line, the yellow line, is higher than the other lines. Actually, really concerningly, in the top right, it's 50% higher, and in the bottom left, it's 100% higher, and I have no idea why this happens. This is something that I wish I understood. And hopefully, in the future, we'll come up with better simulation methods for this, so that this is no longer like a concern. In the paper, we just assume it's 2x. We very prominently say this. So now I'm going to talk about end-to-end simulations of the S state to hopefully get a hold on the T state. So at a 1e minus 3 gate error rate, if you cultivate to distance 5, you can get to 1 in a billion error. You can get this curve goes below the 1e9 line, which is here. Even more interestingly, you can see that this protocol scales really strongly with noise. If your circuit noise was half 1e minus 3, the cost goes down by a factor of 10. And this is because the constant factor is going into the exponent. And additionally, the error is improved by 50 times. The other edge of this is, of course, that if the noise is twice as high, the costs go way up, the fidelity goes way down. So this protocol is incredibly, incredibly sensitive to what is your physical noise strength. This protocol is maybe the best argument that I've seen for why you would want to go to 1e minus 4 noise on your qubits instead of 1e minus 3. I mean, obviously you would take it if you could get it, but this makes a sort of very compelling argument that some component that you care a lot about improves enormously. All right, now let's contrast with other techniques. So at the very first page of the paper, or the second page, I have this enormous plot of all of the previous protocols that I could find that were distilling T-states and put them on left to right as cost and top to bottom as error. Here on the top, you kind of see things that can't get low. These are the injection protocols. They're basically limited to being the same as the physical noise strength. They can't get much below that. Then you have this kind of big blob here of distillation, and cultivation kind of sits between the two of them, maybe shifted a little bit to the left. So this kind of gives you a sense of cultivation is cheaper than distillation, and in particular, in terms of like running like near-ish term fault tolerance computations, like running small scale stuff, this has removed a really, really nasty caustic discontinuity. It used to be, if you wanted a T-state that was, say, 1e minus 4 good, well, there was nothing at 1e minus 4 except, these points over here. And so the cost jumped by a factor of 100 as soon as you wanted to do any kind of fault-tolerant T stuff. And so probably from the perspective of people on the algorithms team, on the Google Quantum team, this for them has been very much like, oh, thank goodness, the cost only goes up by a factor of 3 instead of a factor of 100 if we want to do something that has 100,000 T gates in it. And the title of the paper was that the cost of cultivation is roughly equal to the cost of a controlled knot. The controlled knot is this dashed blue line. And you can see this is very much a regime-specific statement, but they are roughly the same over this range. All right, now I was told that I had to ruin the previous talk, so this is my attempt to do that. Here is a table of gate rotations of the form do a 45-degree rotation around the x-axis or the z-axis, plus or minus. Any series of Hadamard S and T gates can be rewritten into this form. This is not the optimal T-count way of doing a state preparation or of doing a rotation. But if you have cultivation, you can put your target state right in the middle here and then cultivate on all 4 sides and have them take turns basically contributing a T state. And you get this very, very, very compact way of executing this sequence. This means that, assuming the cultivations are reliable enough that this is viable, you really have to start considering the Clifford costs of the more complicated procedures. Because if the more complicated procedure says, I do a CNOT gate, or I do a few CNOT gates, that's going to take much more lattice surgery than what's shown here. Really, my point is that the size of the T state has become sort of commensurate with the size of the lattice surgery, and you kind of have to count both now. So in summary, cultivation is about 10 times cheaper than prior work over this regime up to 1e minus 9 error. And you can push it all the way to 1e minus 9 error, but you can't really push it further than that just because of this post-selection wall. However, it is extremely strongly responsive to improving your physical noise strength. So if your noise strength improves by a factor of 2, then you can get much further than 1e minus 9. You can get 50 times further, and the cost also drops enormously. For me, the most exciting thing about it, though, is that it's so small that you can put it anywhere. I'm used to thinking of factories as these enormous things that you kind of put on one side of the computer, and they produce states, and they travel somewhere else, and they're consumed. But cultivation is so small that if you have a hallway that something else could travel along to get somewhere, it fits in the hallway. So why would you make it over here when you could just make it directly there, and then all of a sudden your routing costs go way down? And that's all that I have.
Okay, thanks, Craig. Some very interesting results. Any questions?
Hey, so thanks for the excellent talk. So I'm curious, I was interested in your comment about you think that it would be hard to drive error rates below 1e to the minus 3.
I'm not an experimentalist, so don't take me too strongly on that. It's more, I don't like asking for things from the hardware team. I like telling the hardware team, you don't need to do this because we can take care of it. And so asking for 1e minus 4 error rates to me is sort of making it harder, making the hardest part of the project harder. That's sort of where that sentiment comes from.
Yeah, I'm curious in Google systems, for example, is the thought that it'd be hard due to either getting the noise out of the environment, is that the dominant error, or the noise of, let's say, crosstalk?
You would really have to talk to a hardware engineer to get a sense of like what the limiting things are.
Got it. Okay.
Yeah.
One other question too. So, as an academic exercise, let's say you could get it lower than 1e minus 3. Under kind of your work here, how significant would that be with your work?
Well, basically at 1e minus 3, it's not quite good enough. So I say here it's like within 10x of being relevant to factoring 2048-bit numbers, because factoring tends to require around a billion-ish gates. So if your error rate is 1 in a billion, then you're going to fail 70% of the time to finish a shot. So 1e minus 4, because cultivating a distance 5 will gain that benefit 5 times, it'll improve by a factor of 100,000. And so then you're just going to succeed. So it sort of is on the cusp of like, if it's 1e minus 4, then you just cultivate. And if it's 1e minus 3, you probably still need an extra stage of distillation. And that extra stage of distillation is actually very substantial. It is kind of a very nonlinear benefit from improving the physical noise. We don't need it, we'd like it.
Got it. Thank you.
Greg, nice talk. Quick question. Can you elaborate on the very expensive decoder you were talking about and what evidence you saw there? Thank you.
Sure. So Chromobius is an implementation of a Mobius decoder. That is a decoder that splits the color code decoding problem into basically 3 subgraphs that are joined at the boundaries, if you're familiar with that. The main limitation was actually that we couldn't get good soft information out of it, or like the things that I tried to get good soft information out of it didn't work very well. Because for this problem, it's very important not just that you get the correct answer, but that you're confident that you got the correct answer, and your decoder is warning you when it's not sure. That's the most important thing. So that was the sense in which it was bad. It didn't do that very well.
Do you have any ideas for overcoming the post-selection wall?
I mean, the post-selection wall is sort of intrinsic to how it's being done. I think maybe people, or at least I used to underestimate how good error detection is compared to error correction. Like I assumed, oh, when I'm error detecting, I can have twice as many errors before I can't tell. But really, because of entropic effects, there's so many ways to have half of an error compared to having a full error chain, that error detection is, like if you actually plot out the logical error rate when using error detection or error correction, the slope of the line on a semi-log plot is not double, it's like double. So it's incredibly beneficial to use error detection. I am personally very skeptical that you could remove it and still maintain the level of performance that we see out of it. Like the Chris Chamberlain paper, that one used error correction instead of error detection. And that's sort of why that they were stuck at 1e minus 4 instead of able to get to 1e minus 3 noise strength and have it work. If you could make that work, then it would be great, because then you could scale it to arbitrary distances, and then you wouldn't have the wall. I think the wall is what makes it work. Yeah.
Okay, I think we need to move on to the next one. So
Next talk? All right.
Thank you, Greg.
We'll talk after.